And it turns out that in either case, the conditional probability, the variance or the confidence interval of this conditional probability is going to be much better than the confidence interval of the probability if you directly estimate A. So let's convince ourselves why that is the case. So the variance of estimating the probability of A, let me just say tilde being like our estimate, right, is equal to the probability of A times 1 minus the probability of A. And if I have a very rare event, then 1 minus probability of A can be basically ignored, just thought of to be about 1. Alright, so that's and also have to divide by the number of samples n. So this is the variance I get if I directly estimate the probability of A. And why is this a bad result? I mean, if probability of A is very small, then the variance is also small. So why is it bad? What's the bad thing about the variance being that? Yes? Oh, the tilde is what I use to denote our estimator to the probability, computed by averaging a number of indicator functions, right? So how can we reconcile the fact that when we have a very rare event, we need a lot of samples, versus that this analytical calculation that says my variance is very small if my probability of happening is very small? So we just said if we have a very rare event, it's very hard to compute the probability of that event happening, because we can sample a lot of samples and none of our samples actually falls into the failure category. But then through our analytical calculation, the variance of our estimator, right, the variance of the estimated probability is the probability of the event divided by n, the number of samples, which means the smaller the probability is, the less our variance is. So why it seems contradictory, right? So I think you raised your hand first.
Because there's also uncertainty in the probability of B that could be small relative to the probability of B, but large relative to the probability of
Oh, here we are still estimating the probability, the estimator if we directly compute the probability. Yeah. Yes.
It's because if most of the time our sample is not going to land in A, then most of the time our estimated probability of A is going to be 0. So the variance is going to be small.
Yeah, that's actually right. Most of the time it's going to be 0, so the variance is going to be small artificially. That's what you guess, right? Anybody have any other interpretations? I think that's a good one, but like my personal interpretation is the following. This is the variance, but what we really care about is how does the standard deviation or the width of the confidence interval compare against the probability itself. So the ratio of standard deviation of the estimator divided by the probability itself is like what? It's like square root of the variance divided by the probability, right? That turns out to be 1 over square root of n times 1 over square root of p. So if P is small, let's say a millionth, then 1 over square root of P is 1,000. It's like it's like you're scaling this number by a large factor if the probability is small, right? So you have a large relative uncertainty if your probability is small. Your absolute level of uncertainty may be small, but relative to the computed probability, your confidence interval is huge. Does it make sense? Okay, so that's the variance you get if you directly estimate the probability. Now, what if you use this formula over here? If you use this formula over here, the importance sampling, so here we assume the B is very easy to sample, so the PB and P not B we assume have very little variance. So the variance of PA, let me use hat to denote the importance sampling estimator. And if we sample these two conditional probabilities independently, then the variance is actually equal to the summation of the variance of these two terms. And because PB and P not B are deterministic, they are just comes out of the variance and squared, right? So it's this times the variance of P tilde a condition on B plus P of not B square times the variance of P tilde a condition on not B. All right.